In this video, I will show you how to find the StateSpace model of the LLC converter. So in order to find the StateSpace model, we first need to define the states that we want to observe, which is X. So IR is the current flowing through the resonance tank, and VCR is simply the voltage over the resonance capacitor. And IM is the magnetizing current, which is the current flowing over LM. And Vout is the output voltage. And we also want to define an input, which in this case is simply V1, which is either VDC or 0, depending on the time and switching frequency. So in order to find the StateSpace model, we just need to find A and B. And these can be defined in two steps. So either when IR is not equal to IM, or when IR is equal to M. So when IR is not equal to IM, we get this one. And if not, we get this one. So I will show you how to find the two different sets of matrices. So now I will show you how to find A and B in this database model. So in order to do that, we need to find x dot, which is the derivative of x. And we need to find it given by x and u. So that is basically what we want to do. So we can start off by finding the derivative of IR, which can be found by looking at the voltages in the resonance tank. So we know that V1 is equal to the voltage over this, plus this, plus this. So we just write that first. So V1 is equal to the voltage over the inductance, resonance inductance, which could be given by the derivative of the current. So we have LR, and then the derivative of the current over time. And then we have Vm, which is a little bit more complicated, so I just leave it as it is. And the voltage over the resonance capacitor is a part of the states, so we don't need to change that. So now we can solve for IR, or the derivative of IR. And then we will get 1 over LR, and then multiplied by V1 minus VCR, and I leave this one to the end, because this one is a little bit more complicated. So in one scenario, it should be equal to the turn ratio multiplied by Vout. That is when there is a current flowing here. So we will just start with that. So we have minus Vout multiplied by N. So you now see that we have this, oh, that was a bad I. So we have the change of IR given by the states and U. Now, in another scenario where there is no current flowing to the secondary side, the diodes would be open circuits, which means that there's no connection between VO and VM. And all of the current, which is flowing through LR, is also flowing through LM. So we know that they're equal to each other, which makes it a little bit simpler. So we can rewrite this voltage again in another way. So we have LR and then DIR over DT. And now we have VM as a function of the current as well. So it's LM multiplied by the change of current again over time, and then plus VCR. So if we now solve for the derivative of the resonance current, we will get something else. Over dt is 1 over LR plus LM, and then multiplied by V1 minus the resonance voltage, capacitor voltage. The derivative of IM. That was not an M. There you go. So now we have found the derivative of the current for one case, and we have found the derivative of the current for the other case, and also the derivative of the magnetizing current for that same case. So we can try to find the derivative of the current, of the magnetizing current, for this case as well. So we can do that. And then we know that it will be equal to, we just simply use the same formula. So we have NVO and then over LM, which is pretty simple. So now we have this one as well. So what we miss now is VCR and VO. So those will be the same for both different scenarios. So I will just continue over here. So you see that. So now we have VCR, which is pretty simple. It just uses the laws for the capacitors. So we have 1 over CR and then multiplied by the resonance current. Because the resonance current is also flowing through this capacitor. It needs to go back, right? So that was also pretty simple. Oh, it's the derivative. I'm sorry. That is also what we wanted to find. And now we also want to find the output voltage. So we can look at the capacitance, the capacitor voltage over the capacitance here, output capacitance. So we know that the change of voltage over time should be equal to 1 over CO, which is the output capacitance, multiplied by the current flowing through the output capacitance. So we know that the output capacitance should be equal to the current coming from the resonance tank minus the current that decides to go to the output. So this would be equal to 1 over C and then multiplied by that current. So the current going from here, is equal to IR minus IM. And then we also need to multiply with the gain of the transformer. So we have N, and then multiplied by IR minus IM. And then we need to do minus because some of the current would flow to the output. Now the output current is defined as V out over RL. So this would be the formula for the change of output voltage as well. So this is real time, I'm sorry, V out. Now by using all of these equations, you can actually find, so that we marked. So this is for one case. This is for when IR is not equal to is equal to IM. And this is for when IR is not equal to IM. Then if you use those equations, you will get these two matrices for the different cases. So you will see that this row is for the capacitor voltage, and this is for the output voltage, and they will stay the same for both of the scenarios. Only the first and the third row would change. So if you plot the step response of the system when the resonance current is not equal to the magnetizing current, you will get these two plots. So this is at switching frequency equal to the resonance frequency. Even though it doesn't look like that, it is. So you can see that it's a little bit wrong, just because we don't actually get a sinusoidal waveform for the resonance current. Because this step response would stop here. Because then IR would be equal to IM, and then we would start with a new step response where this is the model. So then the current would start increasing again, so it would not become sinusoidal. The only way to make it become sinusoidal if the current was going more like this, which is the actually step response of the current. So you can see that it's a little bit wrong, but everything else, almost everything else is correct. So the difference in currents of the difference of the magnetizing current is correct. It should be about 20. And then the capacitor voltage is also almost correct. And also the output voltage is correct. And the peak of the IR is also almost correct if you compare it to Plex simulations with the same topology. So you can see that it's a little bit wrong, but it's kind of okay. So if you don't know how it actually should look like, you should watch this video that pops up here. And just skip the first part because that would be a little bit repetitive.